Hey everyone, it's Ken. I'm here today to give you a couple examples of how to do the substitution rule for definite integrals. So let's go ahead and get started. The first example I'm going to do is something that I've already discussed in a previous video, but in the context of giving a sort of a proof or an explanation of why it's true. And now I want to give you a way to kind of quickly calculate it. So let's go back to this test question. So say that you've got this integral from, definite integral from 0 to square root of pi, and you're looking at maybe cosine of x squared times 2x dx. And you want to apply the substitution rule. And the first thing that you want to think of is what's going to be the change of variable, or what's going to be the thing that you're substituting. Well, you kind of have to imagine what's going to make this problem easier for me. And whenever I see something composed in this function or inside the parentheses like that, that gives me an idea that may be what I want to substitute. And the fact that the derivative of x squared is out here sitting is also another big key giveaway. Really, the substitution that I'm going to want is y equals x squared. And I'm sure there's other substitutions you could do too. And what you're going to do next is, if you remember back in that proof that we looked at before, we had, delta y was roughly equal to the derivative of y times delta x. If you want to write that in what we call differential form, just to remind you of that relationship, you can write dy equals this derivative 2x dx. And that's just, in a way, it's like a rewriting of this substitution that you've made. If y is equal to x squared, then dy dx is equal to 2x, or a small change in y is going to be roughly equal to 2x times a small change in x. And just concisely, you can write that as dy equals 2x dx. Or more generally, if you've got y equals f of x, then dy equals f prime of x times dx. It's kind of a way of keeping track of everything. And then what you can do is you can actually just substitute this in to your problem. Replace all the x's with y's and make sure your bounds of integration, which are for your x variable, get changed to the proper bounds for your y variable. So let's see it in action. You get cosine of x squared, but x squared is equal to y, so that's cosine of y. And then 2x dx, I'm going to ask you to just do the direct substitution. 2x dx becomes dy. And this might be a little confusing if you're really eagle-eyed with this, because you know that the integral sign is not like multiplication, right? You're not multiplying cosine x times dy. What this is it's a symbol that is supposed to remind you that this is a limit of approximations, taking small y intervals, so on and so forth. But in the previous video, we showed that 2x dx can be replaced with dy. And so that's why it's OK, or it's legitimate, to just do this direct replacement in the problem. And so the one thing that remains now is what are going to be the bounds of this integral. X went from 0 to the square root of pi. I'll write that down here. X was bigger than or equal to 0 and less than or equal to the square root of pi, taking the definite integral, or the signed area under the curve, in that range. And so what's y going to be? Well, what's the range of y? So you can just think of just plugging in 0 into x squared gives you y equals 0. Plug in square root of pi into x squared, that's going to give you pi. So your bounds of integration for this integral in terms of y are just going to be 0 going up to pi. And then now you just do this integral like you normally would. The antiderivative of cosine is equal to sine. So take that antiderivative, sine of y. You're evaluating it from 0 to pi. You're getting sine of pi equals 0 minus sine of 0 equals 0. So that signed area under the curve was equal to 0, telling you that there's equal area above the curve as there is below the curve. Okay, great. So let's try one more example. Let's go down here. So I want to do another kind of problem. So let's look at, say, the integral from 0 to 1 of what? Let's take x over the square root of x plus 1 dx. So here's a problem that you might not think initially is going to be very amenable to integration by substitution. But what you really want to do, I think, is just kind of trust the process and see if it works for yourself. So you want to pick, like, what should I substitute? And there's lots of different things you could do. You could try, like, y equals x, and then you get y over square root of y plus 1 dy. And then you'll say, OK, that actually didn't change the problem at all, which kind of makes sense. If you just say y equals x, it won't change the problem. You could do y equals to the, you could do y is equal to the square root of x plus 1. There's nothing particularly wrong with that. I'll let you check that out. But you might find that that doesn't simplify the problem very much for you. When you get right down to it, I think the number one thing that's keeping me from solving this problem is the fact that I've got x plus 1 under the square root instead of just x. And which is kind of frustrating because on the one hand, I can't do the problem, but on the other hand, that seems kind of artificial to me. So by changing the variable from x to y, where y is equal to x plus 1, that's going to remove that artificial difficulty and let us solve the problem in the way that we know how. So if you'll let me, I'll try to do y equals x plus 1. And then I want to say, what's going to be my dy? Well, dy is just going to be equal to dx, because it's the derivative of x plus 1 that's equal to 1 times dx. And so when I do that, when I go back down here and rewrite my problem, so my bounds of integration, x went from 0 to 1, so y is going to go from 1 to 2. And then I have to rewrite my integrand in terms of y. So on the denominator, I get this nice square root of y, because y is equal to x plus 1. Well, if y is equal to x plus 1, then y minus 1 has to be equal to x, right? So I simply get y minus 1. And then it's all times dy. And so this integral isn't so bad. I can break this up into two different parts. I'm going to go, using what we call linearity of the integral. I can write this as integral from 1 to 2 of y over root y dy, and then subtract integral from 1 to 2 of 1 over square root of y dy. And so now I'm off to the races. I'll include one more algebra step in each one to make it easier to find the antiderivative. So I'm going from 1 to 2. And y over the square root of y, that's just equal to the square root of y, otherwise known as y to the 1/2 dy. And then I'm subtracting from it 1 over the square root of y. So that's, you can think of this as like 1 over y to the 1/2, which you're then going to rewrite as y. Getting a little bit of a squeaky marker there. So that we can rewrite this as y to the minus 1/2 dy. So that's a kind of like a tour of elementary functions for us. Just showing how to rewrite the algebra in a way that I can now just use this exponent rule, integrating from 1 to 2 there. Exponent rule from integration tells me that the antiderivative, or an antiderivative for y to the 1/2, is just going to be, well, it's y to the 1/2 plus 1, and then divided by 1/2 plus 1. So that's going to be the antiderivative 1/2 plus 1, that's equal to 3/2. Then I'm going to divide by 3/2, which is the same as multiplying by 2/3. And I'm evaluating that from 1 to 2, and I'm subtracting now the antiderivative, so y to the minus 1/2, so that's just going to be y to the squeaky, y to the 1/2 divided by 1/2. So divided by 1/2, that's 2. old friend of mine had a hamster that squeaked just like that. And so I'm going to integrate this from 1 to 2. And so now you can just plug in and use your calculator. So you're going to get 2/3. And then it's 2 to the 3/2 minus 1 to the 3/2, which you'll find is just equal to 1. And then subtracting 2 times y to the 1/2, which is square root of 2, minus 1 to the 1/2, which is 1. And so, this number is the answer. I'll let you do the algebra to clean it up or plug it into your calculator or whatever. But now that's just another example of a complete solution to a definite integral using the substitution rule.